Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In today's tutorial, I'm going to talk about one of my most favorite topics, which is Gabor filters. And I get very excited talking about these filters because they are very amazing and hopefully you'll see that pretty soon. And especially in the context of image processing and computer vision, these filters are they can be used for texture analysis, they can be used for edge detection, they can be used for feature extraction, which I'll show probably in the next tutorial, where we extract some features and then use a machine learning algorithm to for training purposes. And these Gabor filters are band pass filters, meaning they allow certain band of frequencies and reject other types. And if you don't know what that means, don't worry about it. Okay, we are going to cover exactly what these filters are and how to use them in Python. So let me quickly explain. Well, from a mathematical point of view, what these filters are. Again, don't get intimidated if you don't understand it, because in Python, using this filter is, again, as usual, literally one line of code. Okay, so let me explain what this is from a mathematical point of view. So let's fire up our drawing board and let me write down an equation. And again, please do not get intimidated by this equation. Okay, so first of all, our Gabor is a function of various parameters, like I mentioned earlier. So if I want to write down, so let me start by writing, okay, my G, okay, my Gabor is a function of x and y to begin with. This is the size of my kernel. Okay, so in x and y, this is 2D, obviously, that I'm showing here. And then it's also a function of sigma, which is nothing but standard deviation. Again, think of Gabor as a Gaussian function in 2D. Okay, and it can be 3D and multidimensional. So right now, sigma, okay, it's also a function of theta angle. I'm going to explain again in a second. And it's also a function of wavelength, typically represented by lambda, by gamma, which is the aspect ratio. Makes sense when I show you, and then phi or psi or whatever you want to call that. So it's a function of these parameters. Okay, and it is equal to e to the, I'm just going to write down exponential exp, and let me start a big bracket right there. Okay, so minus, so now I'll take my x squared it, I mean, I can do x prime squared, okay, plus gamma squared times y squared, okay, divided by 2 times the standard deviation squared. Okay, this is the first term in the expression, and the second term in this expression is, I mean, again, I keep saying don't get intimidated by this, but if you understand every little, I mean, each one of these parameters, it definitely makes sense why it actually creates a Gabor kernel of certain size. Okay, so exponential, this is the imaginary term, right? I mean, we learned about imaginary terms in our uh, math back in high school. So 2 pi, okay, times x divided by the wavelength plus the phase, which is represented by phi right there. Okay, excuse my writing here. So this is how a Gabor kernel is described or defined. Okay, now let me quickly mention, so the sigma is nothing but your standard deviation, right? If you have a one dimensional, let's say, Gaussian, then you know what the sigma is. It defines the standard deviation. So that's that term. And if you look at the gamma here, up here, gamma squared, right? I said it defines the aspect ratio. If you look at this term, what is x squared plus y squared when you plot it? This is nothing but a circle, right? So if gamma is equal to 1, then you have a kernel that looks very circular. If gamma is very close to 0, yeah, then you define a kernel that is elliptical in one direction or almost like a straight line. So that's what aspect ratio basically means. Okay, and lambda is for wavelength. So this is basically defining, well, if you actually put this phi term, which is easy to explain, if you have, let's say, a wave like this, let's say, then if you offset, phi is nothing but the phase offset. So it's nothing but, okay, instead of my center being right there, if I offset phi by a little bit, then my center is right there. That's pretty much it. Okay, so it defines the symmetry. So this is mathematical representation of the Gabor filter. So I'm explaining this so you understand changing, the implications of changing x, y, sigma, theta, and others. Now let's actually visualize this in Python. So for that, let me fire up my Spider interface here, and let's just start importing the libraries that we need, and starting with I'll just do NumPy as NP. I don't know if I need it. And Gabor is in OpenCV, so let's actually import CV2, and let's also import uh, matplotlib.pyplot as PLT because I want to visualize the Gabor filter. So now, so this is defined by my kernel size. And next, let's just say sigma. Okay, let's go ahead and do sigma, theta, lambda. So let's go ahead and do that. Theta, LAMDA, well, LAMB, but that's okay. I just typed it. That's okay. Gamma and phi. Okay, so did we do all? Sigma, theta, lambda, gamma, and phi. Sigma, theta, lambda, gamma, and phi, right? So great. Now, one other thing, let me move this slightly. One final thing that we also need to define here is k type, uh, which is the data type. So let me just go ahead and type CV underscore, let's just do 32. And what this means is once the kernel is generated, how do we want to store the numbers? So 32F indicates the type and range of the values. So 32F is nothing but float 32. I'm basically saying once the kernel is generated, store all the numbers as 32. Let me move this out of the way. Okay, so there you go. Now we can see the entire kernel. So let me repeat this. So I'm calling the get Gabor kernel from CV2, and the first parameter defines the size. The second one, sigma, theta, lambda, gamma, and phi, which we'll define in a minute. And k type is what type of kernel values. So in this example, it would be 32 float. So now let's go ahead and define one by one. Let's start with a kernel size of 5 by 5. Okay, and sigma of let's just say 3. We are going to change these values to see how they look like, and theta in radians. So let's just let's do pi by 4. Okay, so which is np dot pi. This is from numpy. I'm getting importing the pi, and 4. This is nothing but pi over 4. We'll change that to 3 pi over 4 or pi over 2 in a minute. And did I use b there? No, just called it lambda. And lambda also, let's just do n pi over 4, np dot pi divided by 4. That's my lambda. And gamma, let's just put 0.5. It's not 1, it's not 0, somewhere in between, 0.5. Oh yeah, one more. Phi equals to, let's just do 0 for now. This is phase offset, so this usually I don't change this by much. This is pretty much it. What's going on here? One dot. Okay, one star. Okay, so this is how we can generate a Gabor kernel. Now let's go ahead and visualize it. Okay, so plt.imshow kernel. Let's run this so we can see the kernel on the right hand side. There you go. I don't know if you can see, but because my theta is np pi over 4, this is actually rotated by 45 degrees. In fact, let's change the kernel size to 50. This is 5 by 5, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is 5 by 5 kernel. That's why it looks that small. So if I change it to 50, now we should have 50 in X, 50 in Y. You see the kernel right there? So at every pixel in our image, this convolutional kernel, I mean this kernel will be applied. So this is how we use Gabor. So now if I change my sigma to from 3 to 30, you can actually see how the sigma, there you go. Can you see it? I mean this, so this is nothing but my kernel size of 50 and sigma equals to 30. So this can be applied. Now, what is the right value for any of this? Well, for the K size, the kernel size, use a size that makes sense to the image and the feature size. Yeah, if your features are smaller, like down to like a couple of pixel level, then having a 50 pixel sized kernel may, you may overlook these features. So just play with this. And in fact, when we generate features, yeah, for our machine learning, we are going to sweep through this parameter space, meaning we're going to create a filter bank by changing the sigma, theta, lambda, gamma, phi, and kernel size if you want to do that. Yeah, if you are okay with the computation there. So you can create a whole bunch of filters just by changing these values. That's why I said this is my favorite filter, digital image processing filter. And if you have this, you don't even need any of the other ones. And you can test it yourself. Now, which sigma should you be using? Again, large sigma on small features means you may miss these small features. Okay, we can apply this on an actual image and then see how it looks like. Now, let's change this to np.pi over 2 instead of 4. So now all of our, I mean, it's horizontal as you can see. Okay, so if I just do np.pi, which is nothing but just pi, right? Now it's all vertical. So if you're looking for features that are horizontal, then by applying this horizontal filter, you're actually passing these horizontal features through and then blocking everything that's vertical. Exactly vice versa here. I'll show that on a real example in a minute, okay? Now, so let's change this theta to np over 4, so that's okay. Now let's look at this image. So that's how it looks like. Now let's change this to change lambda, which is nothing but our wavelength. As you can see, it's changing over there, and now I change it to pi over 16. So let's see how the wavelength effects. As you can see, I mean, you can clearly visualize the wavelength change between these two images, keeping everything else the same. Yeah. So I usually put it to pi over 4. Okay. Now gamma, again, let's go back and apply this, and let's also go back and make our sigma to be 3. Let me run this so it's easy for us to see. Now you see how the aspect ratio, is right here. So now if I change the gamma to 1, again, I explained to you earlier on the drawing board, if we change gamma to 1, that means it's nothing but x squared plus y squared, which defines a circle. So our aspect ratio reflects a circular kernel. I don't know if you can see it, but that's more on the circular side. Okay, so let's go to a kernel size of 10. I don't know if that makes it, no, that doesn't make it better to visualize. So let's go back to 50. So hopefully you can visualize this right there. If I go to gamma of 0.01, almost 0, right? So now I should have like a very elongated kernel. As you can see, that's the aspect ratio. So this is more circular, this is more elongated. Again, which one is right? It completely depends on what you're trying to extract from your image. And Gabor kernels are amazing for texture. If you have two different regions with very similar gray level, but you can see it, but you cannot extract them, separate them, using any of the other digital filters or your histogram, try Gabor filter. This works like charm. So 0.5, let's go back, and phi, again, let me run this. So this is how it looks like. Keep an eye on this bright streak in the middle. If I change this to 10, for example, it offsets it, right? So now we should see maybe something shifted, right? Everything is shifted. Now I see something dark in here. So it's nothing but you have a wave and it's shifting it by whatever that 10 units, okay? So I usually don't care much about this phi. I hope this part explains what the Gabor kernel actually is. It's nothing but a bandpass filter where we are defining various parameters of this bandpass filter, including the kernel size, the sigma, theta, lambda, gamma, phi. So now we create, in this case, now we have actually created a digital filter effectively. Yeah, we are getting a bit close towards deep machine learning where you have a whole bunch of filter banks. Okay, but here, of course, we are doing one by one. I'm changing one at a time. Okay, so this is our kernel. Now, what does that actually mean? Okay, you can see this kernel. How does it look like, and how is it going to affect your image? So let's go ahead and open an image and apply this kernel and change a couple of things to understand how this actually works, or how this filter helps us extract relevant features. Okay, so for that, let me remove the plt.imshow. Well, actually, I should have commented it out. But let's go ahead and start importing our image, and let me import the same BSC image that I've been using in most of my videos that I downloaded from the internet. So cv2.imread bse underscore image.jpg. Okay. Uh, and in case you wonder how it looks like, let's go ahead and look at cv2.imshow, and I'm going to call this original image, and this is img. Okay, and do not forget to cv2 dot, where is it, weight key, weight, uppercase K, EY, and I'll leave it, the image box, open until I close it. Same thing with destroy all windows. Okay, there you go. So let me go ahead and what is it saying? Okay, let me go ahead and run this so we can actually see. This is the image, input image. Now let's see how this image looks like once I apply this kernel. And you probably remember from one of my previous lectures how to apply a specific kernel on your image. It's nothing but, let's say, first of all, let's convert this image into gray. Okay, so which makes it easier. CVT, uh, uppercase C, color, and we are applying that on our image. And how are we converting it? Color underscore BGR. Again, this is OpenCV, so it's not RGB. BGR to gray. Okay, so there you go. And now let's apply this Gabor kernel. So let's say my filtered image, I'll just call it FIMG, filtered image, is CV2 dot filter 2D. Okay, this is how we apply a kernel to our image, and using what? CV2. I mean, let's actually define. When you look at the documentation for cv2.filter2d, it takes like these arguments, cv2 8, let's make it uc. So this is nothing but unsigned 8-bit. uh, did I type it wrong? C3. And what do we want to apply? We want to apply this kernel to our image. So first of all, let me run this to make sure I haven't made any mistakes. If everything looks okay, now let's go ahead and visualize. What do we want to visualize? Let's actually visualize our filtered image. Okay, and that would be FIMG. That's my filtered image. Well, let's also look at the kernel because I deleted the line up there. Let's go ahead and do uh, kernel, and this is nothing but KERNEL. There you go. Okay. Uh, Actually, because the kernel may be too small, let's resize the kernel to the right size. So let's actually do. Otherwise, I mean, our kernel can be, if I do only 5 by 5 pixels, then our image would be humongous and the kernel would be only 5 by 5. So it would not look pretty good. Okay, so I'm just gonna do kernel resized. Okay, and let's do cv2.resize, and to what size? I think our image is about what, 750 by 1000. I don't want the kernel to be that big, but somewhere around 400 is okay. uh, so resize my kernel to a size of maybe 400 by 400. It's a symmetric kernel, so that should do. Okay, so now let's actually visualize this. Okay, so anyway, all we did is generate a Gabor kernel for using the parameters that we defined up here. Okay, and applied it on a gray level image by using our cv2.filter2d method. Okay, and we are resizing our kernel to 400 by 400, so it makes it easy for us to see. That's pretty much it. So let me go ahead and run this, and here is the input image. Oh, it's on my other screen. Let me drag it. Here is the kernel, obviously resized, and here is the filtered image. So underwhelming, right? After all that built up, after all that I mentioned about Gabor, this is what I'm showing you. This is not cool. Let's use a different image so I can show you the effect of these the Gabor filters, uh, which makes us understand this image a bit better. So for that, I haven't found a great image anywhere. So I actually created my own and I called it synthetic.jpg. Okay. In fact, if I let's not look at any of this. If I run this, you can actually see how my synthetic image looks like. Again, it's not that great of an image, but I just put a bunch of horizontal lines, angled lines at positive plus 45, negative 45 degrees, vertical lines, and a mixture of this. And hopefully this can help us understand the kernel a little better. So now, if I go ahead and undo this, so because my theta here is n pi over 4, which is 45 degrees, I'm hoping we should only see the lines that are 45 degrees. So let's go ahead and run this. There you go. There is the kernel, and there is the resultant filtered image. Isn't that amazing? Even though I have lines going in both directions here, I'm only pulling the horizontal lines that are aligned along with my Gabor kernel right there. All the other lines, this image is suppressed. Now, hopefully it makes sense to you what I mean by band pass filters. This is the band, it's only passing the things that it lets them through, and anything that's the other direction, it's completely blocking. The horizontal is gone, the vertical is gone. Yeah. So you see, like it tries to show some little things, and that can be played. You can suppress these little, I don't know, regions right around there by changing the kernel size. In fact, if you change the kernel size by a lot, for example, let's go to 50, okay, then it will not do a great job because my pixels are too small. You see, that's how the filter looks like. And you see, we see a lot of artifacts like right there, artifacts right here. So it it helps if you know what you're looking for and you can engineer the filter such a way that you extract the right features out of it, or just generate a whole bunch of filter banks and use machine learning algorithm to detect these. So let's go back to a kernel size of 5 just for the fun of it. Let's change our theta to np.pi over 2. Let's run it, and there you see it's why am I not picking things very well right there? Okay, I don't know. We may have to play with a few of the other parameters that we have here to see what we can actually, how we can uh, improve, on our maybe changing the gamma to 1.0, maybe changing the phi. But I hope this explains, just for the fun of it, again, one more time, let's do this 3 pi over 4, right? So 3 pi over 4, let's go back to 1 pi over 4, first of all, so you can see that we are only looking at these horizontal ones, right? So 3 pi over 4 means this entire band is turned around by 90 degrees in counterclockwise. So we should see only the ones in this direction, in that horizontal direction. So let's do that. 3 pi over 4, run it, and there you go. We are only seeing the ones that are the other in the other direction. Okay, so as you can tell, I cannot stop playing with this. NP over 2. Let's run it. And then this is the horizontal. We already did that. How does it do with vertical? NP pi over 1. And then how does it work with vertical? Looks like we need to do something else, like maybe change the wavelength or change the phase by a little bit to get these vertical ones. But please feel free to play with this and then make sure you find like the right type of image to test this thing on. So I hope now it makes sense, at least what Gabor filters are and how to generate these Gabor kernels. And in the next tutorial, I'm going to actually generate a whole bunch of these Gabor kernels and then train a machine learning algorithm on these so we can apply it on other images on untrained images, let's say, to perform some segmentation on them. Okay, so I hope you found this tutorial to be educational and useful. If so, please like this video and subscribe to my channel. Thank you very much for your attention.